Hey everybody, welcome back to another episode of the problem solving series. Today we're going to be introducing, I think, what I'm going to be calling a sub-series within the series. So the kind of overall theme for these types of videos is going to be there's only so many ways that you can ask a physics problem. I'm going to follow the structure of this video and how these videos will typically go. I'll start with the basics, then introduce ways that you can add complexity, and then for those complexities, how we break them back down into basics. And today we're starting off with kinematics. This will include 1 and 2D since the equations for both of those are the same. And in my mind, I feel like the 2D kinematics is just 1D kinematics, but with an added complexity. So that's going to fall into kind of the first level of added difficulty. But first we'll go through the equations. Okay, so the first thing I want to take a look at are the equations that we have for kinematics and for object motion and how we can use them. So these three equations here are only going to be used, don't have my pen up, when we have constant acceleration, and that will include when acceleration is equal to 0. Some terms will drop out, but we could still use these. When this is also going to be only for a single object, so one object gets their own set of equations, and this is also going to be along a single dimension. So as in the 2D case, and as you guys start to learn the 2D kinematics, which if you haven't gotten there yet, you'll get there soon. But everything that you're doing in 1D with these equations along either the x-axis or the y-axis, so either horizontal or vertical, you can have an object moving in x and y at the same time, and the motion in each of these dimensions would be described by this. So oftentimes you might see, instead of an x, you can also write that as a y. And sometimes they'll even include on the velocity like that, that's Vy times delta t plus 1/2 Ay delta t squared. So sometimes there's that distinction, but either way, these are the equations that you would use for each of these situations. So let's take a look at how this plays out in an actual problem and what the simplest boiled down kinematics question that we can have. So the absolute simplest type of question that you can get that just uses the equations is some object, and they have to give you at least 3 out of the 4 variables, either from the top equation, I didn't quite mean to do that, either from this top equation or from this bottom equation. Because remember, in order to solve for anything, we need to at the very least, have 3 variables. You could have more than that. I think there's 6 variables total in this whole set of equations, but you need at least 3 from this top or from this bottom to be able for them to ask for anything. And then with those 3 givens, then you could pretty much solve for any other unknown variable. So I'd say like one situation is that you're given VF, VI, and A. You can use those to solve either delta X from the bottom or delta T from the top. Or any other, basically any other kind of combination of those. So you could also be given, I don't want to go through all of them to spend that much time, but another option would be, say that you're given VI, acceleration, and delta t, and then you could use that. They could ask you for VF. They could also ask you for, this, you could also get delta x from this. Then you would use this equation. You could get, I think that's all that you could get from that. But yeah, hopefully you get my drift here. So basically they have to give you at least
3, and then you could go from there. They could give you more just to have a little bit extra information, and maybe you have less steps. So yeah, so essentially these are some of the types of problems that are going to be the absolute simplest that you can cover.
Okay, so now that we've gone through kind of this really simple question and that's basic structure, now let's talk about some of the ways that we can add complexities. So one of these ways we saw in discussion for week 2 in P201, and that's to have two objects. If we have more than one object, I guess it doesn't even necessarily have to be two, right? It just has to be more than one. So if we have more than one object, then each object is going to have to get its own set of equations in a single dimension. So again, I'm going to keep things single dimension just for this, but even if you have a truck and a car, that was the example that we had, and this is going to be the car and this is going to be the truck, and they each have some sort of set of motion equations that are going to describe their individual motions. So they each need own set of equations. So this might also be linking back to bookkeeping at the end of the first video from this series. This would be where you want to distinguish which variables go with the car and which variables that you're given that go with the truck, because if you mix them up and they have their own equations, then you're not going to be able to get the right answer, since those equations are only valid with one object at a time. The other thing that we could do is you can have different accelerations at different time intervals. So I feel like one that's really common is that you would say that a car is, from t equals 0 to t equals 5 seconds, or we'll keep it even more general than that. You have a car that's going to be going at a constant speed for a given amount of time, then it sees that it has a red light, and now it's going to start decelerating and come to a stop. And you want to know from the time that the interval started, according to the problem, how far does the car go in that time. So that would require us to, again, set up two different sets of equations, and we want to have one for the first time interval, so I'll say 0 to t1, and then t1 to t2 is the second one, where in this one a is 0, and because I didn't get numbers, I'll just say this a is not 0, or a is negative, since that's the example that I gave. So each of these would get their own set of kinematic equations. You would solve for the position, given that you have other information that you need. You'd get the position from here, which you could call x1, and you could get the position from here, which would be x2, and then if you add those two together, then that would give you your x total. The last thing that I said that, again, relates right back to the context in which you can use these equations is that you're going to have more than one. Ooh, what am I writing? Writing them in the wrong order. You can have two dimensions. So the simplest example of having kinematics in 2 dimensions would be a single object undergoing projectile motion. And in that, you want to keep your y variables separate from your x variables. But something too to keep in mind is not only what things you want to keep separated, but for this in particular, what you want to keep the same. So something that's really, really common and is a tactic that could be used for any one of these is that now that you have two sets of equations that you can use, they're more likely to add in multiple steps. So I'll start with the projectile motion example because I think that that's the most common one that I see, is that you'll have some information from y, you'll have some information from x. The problem will ask you for something, let's just say in the x, say it's asking for what the x position is that a projectile makes in the total trajectory that it makes. We want to know the total x. but they don't give you enough information with just x variables that you could solve for that right off the bat. So typically what they'll do then is give you enough information in y that then you could solve for time, because the time that it takes for this object to make its journey up and down as it's traveling in this arc is the same amount of time that it has to make that horizontal change in position as well. So typically the way that I set these up, and I have like no space left on this page, but I'll usually do my x givens, I'll set up a table, do my y givens, and then, you know, write what those guys are there, and underneath the chart I'll write what the t is, since that's the thing that's shared between the two of them. So, I mean, if you're fancy and you want to draw Venn diagrams, then t would go in the middle of what's in x and what's in y. Okay, so with all of that being said, you can also have combinations of these things in conjunction with each other. So you could have more than one object undergoing projectile motion at the same time. You can have two different objects having two different time intervals where they're doing stuff. You know, there's these things are all interchangeable or could be combined together. But the important thing is to just be able to break down where your equations are valid, so where you can use the tools that you have, and then again, bookkeeping to keep the things separated that you want to keep separated, so that they go with each other in those equations. Last two things I'm going to mention are just going to be two pieces of information that come from equations, but conceptually, if you can memorize them, they make things go a little bit faster, and I do think they make a lot of physical intuition once you sit and think about it. So the first is going to be that if you have an object, this is both of these are going to be related to vertical motion. So if you have an object that is in free fall, so let's just say it goes up, it reaches some max height, and then it falls back down. There's two things that we know right off the bat about something like this. So the first one is going to be that when you're at your maximum height, your velocity is going to be equal to 0 vertically. So I'll write Vy equals 0. That will always be true in free fall. So when you're at that point when velocity goes from positive to negative, then it has to pass through 0 in order to do that. The other thing is that if you're in free fall, and again, constant acceleration is a key component here, then the time to go up is going to be equal to the time to come down. So these guys are going to be equal to each other and interchangeable. Sometimes having this information can help solve problems where that is not explicitly written in the problem, but you have to make use of it in order to solve what they're asking for. So that's something that I would highly recommend that you put on your cheat sheets if that's something that you don't think that you'll easily remember or just need to see a couple times, so that way you can memorize it and get that in your repertoire. The other thing that I'm sure that many of you might be asking about, since this is the kinematics video, is going to be about the position, velocity, and acceleration versus time graphs. I have an entirely separate video on that that I'll put in the cards, so that should pop up. I'm gonna get out of here. Happy physicsing. We'll go to Howitzer for the goodbye clip and a little bit of cheering up after having to watch a physics YouTube video with me. So enjoy. I hope you guys found this video useful, and I will see you guys in the next one. Howitzer, you gonna say bye to the kiddos? You want me to take you for a walk?